I'd like to begin by thanking the organizers for their hard work in putting together this conference and also for the invitation to come and speak here. Now, this talk will have a very different flavor from those you've heard already today, and I'm quite confident also of the two remaining talks that will follow. And it's work in progress with my former student, Sebastian Pögel, who's now a postdoc in Zurich. So we're going to be looking at Yang-Mills amplitudes, and more particularly, we're going to focus on one-loop all-plus amplitudes in pure Yang-Mills theory. And we're going to do some exploring. Now, I realize that the word syzygy may not be in everyone's everyday vocabulary, so I thought I would put up a definition for it. Now, the original definition, in fact, is that of a straight line or nearly straight line configuration of three celestial bodies, three or more celestial bodies. But in spite of the gravity connection here, that is not the meaning which I'm using it here. It's very popular these days to always go to AI for some definition. So that was what I did next, and that gave me the mathematics definition as an object that describes the relationship between elements of a left A module. Now, I'm sure that clears it up for almost everyone in the audience, but in the case that there isn't, I thought I would give a more pedestrian definition, which is in fact the sense I'll be using it today. A linear relation between amplitudes where the coefficients or the elements are polynomials in the Mandelstam. Now, if we go back for a minute to tree level, we have an expression to be summing, right, the full amplitude as a sum over the non-cyclic permutations with the reflection modded out. That's what the over 2 is. Trace factor times the color ordered amplitudes. And there we know, and I hope at least many of the people in the audience love the various identities that we know. There are identities where the elements are constants, the photon decoupling identity and the Kleist-Keif identities where they're of group theory origin, and of course the very celebrated Bern-Carrasco-Johansson identities where the elements are linear in the Mandelstam invariance. We're lucky to have all three of the authors sitting somewhere in the audience. I don't see where Tzvi is, but so these identities are helicity independent, and they have the form where we write it as a sum over the set, usually, in fact, full, doesn't have to be, but I'm going to think of it as being the full set of non-cyclic permutations of amplitudes with some coefficients. And the amplitudes here are really functions of the permutation. You simply permute the indices of the momenta to get the other amplitude. That's not true for the polynomials. You really should think of sigma here as just a label. Okay, what about one loop? Well, there we can write the full amplitude as the leading color parts, single trace, and then there are sub-leading color parts with a double trace. And there's an identity which Tzvi, Lance, and I wrote down in a paper many years ago, relating all the sub-leading color amplitudes to the leading color amplitude. Again, it's of coefficients that are constants, and it's helicity independent, and it's of group theory origin. And as we'll be seeing, there are other identities that can also arise here. These are generally helicity independent, and they have the same structure because we can eliminate the sub-leading color ones with just constant coefficients. We'll focus just on the leading color amplitudes. So these syzygies were in fact studied many years ago by a quartet, in fact a trio of whom are again sitting in the audience, Emil, Henrik, and I don't see where well, Henrik is, but maybe he's somewhere here. And there's a fourth gentleman whose name is best forgotten for reasons that you can ask Paul Henrik in private. And they found any syzygies with the constant coefficients. This is just one example of them. You sum over a certain shuffle. Oh, that way. So you sum over a certain shuffle product, and then there's one additional term with just the permutation in the naive order, and that sum gives you 0. In fact, they also counted the number of these identities. It's in terms of this combinatoric object written with the square brackets, which is something called the unsigned Stirling number of the first kind. If you want to know what that is, look it up. Now, in this case, there are no syzygies of degree 1, but they did find examples of syzygies of degree 2. So these are polynomials which are quadratic in the Mandelstam invariance, and the coefficients here are maybe a little bit random looking. There's no great commonality between the different coefficients, and these relate 6 different amplitudes. But what's interesting is that they found 4 independent amplitudes, so that overall the number of independent amplitudes is 2. And they also looked at this at 6 points, and there, after all the dust settled, they concluded that there were 3 independent amplitudes at 6 points. So I guess from the fact I'm talking about this at all, you can conclude that there is in fact more to the story, but the question is there more to the story? And so the answer is yes. Well, this was done quite a while ago. In fact, if I recall correctly, you were a postdoc at Saclay back then. Yes, so there's a Saclay connection to the origin of these syzygies as well. So Costello computed the amplitude in a theory with a specially chosen matter content, 8 copies of fundamental plus anti-fundamental, and 1 copy of the anti-symmetric and anti-anti-symmetric. Anti-symmetric representation SUN is the generalization of the 10 in SU5. And this was motivated by, I think, some anomaly cancellation in some higher dimensional theory. I forget exactly what the reason was. But the thing that was interesting is that he found that this amplitude vanishes for this particular chosen matter configuration. And very recently, Lance Dixon and Anthony Morales, his graduate student, shows that these imply the degree 0. This vanishing implies the degree 0 identities that the Copenhagen people had found many years earlier. I don't know, by the way, if Anthony Morales is actually on the job market or not, but if so, you should probably keep an eye out if you're hiring. Okay, well, this is nice, and maybe we'd like a little bit more. So let's actually step back and take a more generic view. So we're starting with a set of n-1 factorial over 2 amplitudes. And let's do the following exercise. Let's first of all multiply all of them by, each one of them by the common denominator set. And then after that, let's find a spinor factor that removes the spinor weight. So starting with all plus, it will typically be something with brackets in it instead of angle brackets. And that result now is some polynomial in the spinors. We can re-express it in terms of Mandelstam invariance and a whole bunch of Levi-Civita symbols. And it's going to be linear ladder because the square of, or product of 2 Levi-Civitas can always be expressed in terms of Mandelstam invariance. We can then choose a basis, momenta 1 through 4, if you'd like some other set, and we can then re-express the momenta and the other Mandelstams in terms of the standard basis. And that'll introduce some new denominators in terms of four momentum gram determinants. But we can clear those gram determinants as well, multiplying again by the common denominator. And the result of this somewhat heavyweight series exercises is that we get a set of polynomials, and each polynomial has a set of terms which are free of Levi-Civitas, and a set of terms which are linear in one particular Levi-Civitas. And because we're looking for identities where something, a sum over a certain set of things is 0, all this multiplication and doesn't make any difference. And so this set of polynomials now satisfies the same identities as the original set of amplitudes. Okay, so what are those identities? Well, let's look at any three polynomials. It turns out there's an identity. And if we write them in the general form, let's say each there's the epsilon free and then there's an epsilon term, then basically by constructing the determinant, you can write down a set of coefficients, A1, A2, and A3, and A1, A2, and A3 form a syzygy. That is, it gives an identity for these three polynomials and therefore also for the three original amplitudes from which they emerged. Now, those of you who have been thinking in parallel to listening to me go through this argument have realized that this then means that there are going to be, in general, for our original set of amplitudes, n minus 1 factorial over 2, they're going to be n minus 1 factorial over 2 minus 2 syzygies. So we're always going to have two independent amplitudes, except for the 4-point case where there'll be just one. Okay, so there's an existence proof that we should always expect just two independent amplitudes. But these syzygies are not the ones that we're really interested in, because they're a very high degree. All this multiplication, in general, I mean, it depends on the details of what exactly we pick, but in general, it's going to scale, the degree of the polynomials is going to scale like n squared. So that's not what we're really after. And again, those of you who have been thinking in parallel will have realized that the argument I just gave doesn't really care about the fact that these are amplitudes. It would hold for any rational function, set of rational functions where we have a common spinor weight and a common energy dimension. So the question we should be asking is, what is special about amplitudes? Of course, in this audience, I would imagine that there are many answers to that question. There are many things that are special about amplitudes, especially here. But the things that I'm going to exploit is complex factorization, in fact, complex factorization. And in the case of the amplitudes we're looking at today, the all plus amplitudes have only simple poles in the angle spinor invariance. So we're going to make use of that. So we're trying to find a set of polynomials that for the endpoint amplitude. And again, sigma here is a label. We're multiplying them by the amplitudes as a function of that permutation and summing over the independent set of non-cyclic reflection-free permutations. And we want that sum to be equal to 0. So let's take the residue at some pole, at the pole in the angle bracket ij of both sides of this equation. So the right-hand side is 0, the residue is 0. So, and on the left-hand side, what's going to happen? Well, the amplitude is going to factorize. In this particular case, it's going to factorize into an n minus 1 point amplitude times a 3-point amplitude. And there's going to be, in general, more than one permutation, in fact, in general, two, that will give rise to the permutation of n minus 1 lengths. There's also going to be a sign that's associated with the ordering of ij in the original permutation and whether or not there's a reflection involved in reducing the ij to the common momentum, the sum momentum k. Now, in this particular case, it's going to be after we take into account the sign that puts the 3-point amplitude into this canonical form, it's going to be the same 3-point amplitude that shows up um, everywhere. So we can divide it out. And then we get the following equation. Now we have a sum over the non-cyclic reflection-free permutations that correspond to the n-1 point amplitude, and there's a sum over the n-1 point amplitude, the different permutations. And then there's this object inside parentheses. And you'll notice, of course, that this equation is exactly the n-1 point version of the original equation we're trying to solve. So we should think about doing this recursively, or deductively, however you want to think of it. And so in solving the n-point equations, I will assume that we've already solved the n-1 point equations. And if you want a starting point, then the 4-point equations are simple enough. You can just solve them by hand. So we can now write down the general solution to this equation by setting this equal to some sum of now what are now the known polynomials for the n-1 point amplitudes. So this is the solution on the pole. And we simply write that sum. So it's a sum over, in this case, over two permutations that give rise to the daughter permutation, whose reduction gives rise to the daughter permutation. The sum with some computable sign is going to give you some sum over the syzygies of the n-1 point. This f here is in general, some polynomial, arbitrary polynomial. Now, we of course have many different poles, and we expect that in order to fix the structure of this function, we need to consider not only the pole at one particular place, but all the possible poles, which in fact correspond to all the different angle products. And in addition, we expect there's some behavior at infinity. One can study this by simply thinking about the spinners moving around in the complex plane, but if you want to use the crutch of doing a BCFW shift, you can do that as well, and then the z goes to infinity limit is the remaining degree of freedom that we would need to fix. So we can extend this away from the pole by promoting the momentum k to the sum of I plus j, and also adding something that vanishes at the pole. And again, ordinarily, if one was doing a real pole, there would be other polynomials that can vanish on the pole, but here we're really insisting that the angle bracket vanish, so this is the correct choice. So for each of the poles, we now have an equation like this, and we have to combine these equations and solve this set of equations together. So we have a set of equations, and later one can impose the z goes to infinity behavior, the behavior at infinity, for example, numerically. There are other ways of doing it, but if you want to think about it, that's a reasonable way to do it. Okay, so now the question is, how should we go about solving these equations? So the first thing that you would probably think of is you write down an ansatz and you solve for the coefficients. And that is, in fact, a perfectly legitimate and feasible way to do this for a small, low multiplicity and low degree d. But as these things grow, then the matrices have a number of rows and also a number of columns that you have to solve, which grows rather formidably. I mean, this expression looks maybe a little bit intimidating, but the scaling behavior is something factorial times n to the 2d. So that quickly gets out of hand. And to quote our chopstick covers from one of the previous days, that's something that is simple but not easy. So instead, we want to look for something which may not be so simple, but is easier, or at least feasible. And that something is computational algebraic geometry. And I realize that that also is not something which is necessarily an everyday usage by most members of the audience. How many people here actually use computational algebraic geometry? One person? 2 people? 3 people? Okay. Anyway, So in spite of the very limited amount of time, I thought I would give kind of at least a lightning foreign language lesson for those of you to whom it is indeed a foreign language. Now, I'm fairly confident that there's no native speaker of this particular language in the audience. So, so fewer than for the computational algebraic geometry. So the basic objects that we're studying here are systems of polynomials, and you can think of it as systems of polynomial equations where we're setting some number of polynomials to zero. There's also a complementary view in terms of the surfaces that these define, and they're in multiple variables. And it's the multiplicity of variables that really distinguishes this enterprise from the synthetic division that I assume everyone learned in high school. So there's some set of basis polynomials, which are called generators, and the coefficients here are numbers, or maybe they're rational functions of other variables. Here you can think of them as rational functions of perhaps other parameters. And we're going to consider all polynomials that are built out of them. So we multiply our generators by essentially arbitrary polynomials in the same variables. And this object is called the ideal that's generated by the original polynomials. Now, in the case at hand, what we're interested in are actually what physicists call vectors and mathematicians call modules of polynomials. And if we take each of the unknowns across all the equations, then that will give us a set of vectors which have fixed coefficients. They're given, for example, by the coefficients of the f's. So they're given by the known syzygies of lower degree. And the question here we're asking are, what are the syzygies of these polynomials, or in our case, the vectors? So in order to solve them, we need to choose an ordering of the modules. Again, that's the thing that kind of is unusual and tricky. And also, in our case, an ordering of the different vector elements. And we build something called a Grosvenor basis, and it's a special set of generators that allows us to answer this question. One of the reasons it allows us to answer this question is syzygies are elementary in terms of the Grosvenor basis, and we can then translate them back to our original vectors using something called a cofactor matrix, which also the formalism teaches you how to do. There's one thing I should point out. Usually in physics, things are named after the people who did them, or perhaps if you believe the Arnold theorem, the last people who did them worked on them instead of the first people. But Grosvenor basis is a little bit different. How many graduate students are there in the audience? Can we have a show of hands? Yeah. Okay. So the Grosvenor basis actually was invented by a guy named Buchberger, who was Grosvenor's graduate student, and he named it after his thesis advisor. So that's a lesson, I think, for all the graduate students in the audience. Anyway, these kind of building and the using and lots of utilities are actually implemented in a system called Singular, where there's a nice mathematical interface, and it's also in other computational algebraic geometry systems. So we use those, and we get a set of solutions. First of all, we don't have to put in an ansatz. Whatever degrees come out are the degrees that the solutions exist. They don't necessarily come out in the simplest form, and so there are presumably additional constraints or some hand polishing that's necessary. That's still an open question for us. But we indeed find that, for example, at 5 point, there's 6 degree 0 solutions. At 6 point, there's 25 degree 0, which agrees with the Copenhagen numbers. And there's 4 degree 2, which again agrees with them. But there's 33 degree 2 in the 6 point case, which is one more than they found. So in fact, these saturate the number that we expect from the general argument. And although I didn't write it down, it does, we don't have an all n formula, but we're fairly confident. We've also checked 7 point, fairly confident that this continues. And in the 5 point case, we find that the simplest identities you can write down actually have, for the degree 2, have 5 rather than 6 non-zero entries, and the entries have this tantalizing and relatively simple looking form of certain cyclic kind of terms of products of invariance with plus or minus 1 as coefficients. So that's, and there are clearer generalizations, which I'll come back to in a while, but there's another syzygy, which I think everyone here knows from, well, for the younger people, it's from the lectures and from ancient history, I suppose. Some of us old folks, we learned it by seeing it emerge. And that's, of course, if we introduce the gravity amplitude, which I'll write as n, and from the same general argument, we know that there has to be a relation that connects the gravity amplitude. In this case, in order to get the right spinor weight and dimension, we need to multiply 2 amplitudes together, and there'll be some set of dimensionful coefficients here. As long as f, this coefficient of the gravity amplitude, is a polynomial, we're guaranteed to have a syzygy of that form. We don't know what dimension it would have to have. But we're not guaranteed to have it if we want the coefficient of the gravitational amplitude to be minus 1. Now, at tree level, we in fact know that there is such an identity, syzygy, and it's of course the celebrated KLT identity, which has played a very important role also in the gravitational wave part of the story in the last few years. So the question you might ask is, what about one loop? And the answer is that we in fact do get a similar relation for the one loop all plus amplitudes. So we sum, in this case, 2 permutations over all this is over the complete set of non-cyclic reflection-free permutations, and there's a matrix of the appropriate dimension. It's 1 dimension higher than at tree level, so it's degree 2 in the Mandelstam's for 4-point, degree 3 at 5-point, degree 4 at 6-point. And we've checked for 4, 5, and 6-point that there is such a solution. We don't, again, have an all-in form, nor in fact proof that it exists, but we have some faith, because 6-point already is fairly non-trivial. And it turns out that for the 4 and 5-point cases, one can also find very simple forms that we can just restrict attention to the permutations where there are 2 common poles between the amplitudes. And then in the 4-point case, we can just choose the product. There's some numerical factor in front, but some product of those 2 poles. In the 5-point case, there's a simple linear function of the other Mandelstams and vanishing in the other case. And again, for the 6-point, we don't yet have a simple form, but there's I think one can be found. And the other thing that's kind of interesting is that one can make this kernel, this one loop KLT kernel, one can make it manifestly Bose symmetric, which didn't have to be that way, but it could be, although finding that form is not necessarily trivial. So with that identity, let me come to my concluding slide. So their scattering amplitudes actually have a lot of identities. And in the particular case of the all plus amplitude at one loop, and there are other examples which we've not explored exhaustively, these are actually very simple, degree 0 or degree 2. And there's a generalization of the KLT relation to the all plus one loop amplitude. And on general grounds, of course, we know that there are going to be some identities also for integral coefficients, both between different integral coefficients and relating Yang-Mills to gravity integral coefficients, and also for rational terms, at higher loops. But we're not sure, but we think that many of these will be of relatively low degree. In fact, we know that for the rational terms in the two-loop all plus amplitude, there are in fact simple identities of this form, and that's in fact where this project got its start. So with that, let me stop here, and thank you.
Thank you very much, David. Any quick questions?
Thank you very much for this great and entertaining talk. So for the generalization of KLT at one loop, do you think you can see an interpretation using intersection theory?
So I would say that what we've seen thus far is that the degree 0 identities, there's some likelihood that they will have a group theory interpretation, even if it's not obvious. Now, obviously, there's many such identities as Paul Henrik and Emil and Henrik will tell you, even for the 1 minus amplitudes at one loop, and I can tell you that there are also such things for two-loop rational functions, things like that. So it's unclear if they will all have a group theory interpretation in some obscure way or not, Dixon-Morales type interpretation. So the question that's left over is, what is the origin of these identities that have low degree polynomials? And yeah, I think exploring an intersection theory explanation is an interesting direction to go. I don't know the answer to that question. You need to turn on the mic.
Thanks for a nice talk. Have you tried it with the non-factorizable terms of the O plus at two loop, if any of this works?
I'm not sure what exactly you mean by non-factorizable. What we've looked at are the rational terms.
Yeah, so the non-rational terms. Have you looked?
So the answer is no. And but again, as the general argument shows, is there's going to be some relations between the coefficients of the integral functions.
Yeah, my question comes because you can write the O plus at two loops in terms of things which are inherently like one loop times some factor that takes into account some divergences. So I think it should work out of the box.
So yes, then to the extent that the one loop is embedded in there, there will be more identities than just looking at the coefficients of integral functions. But we haven't looked at it.
Thanks.
Hi, David. Nice talk. Can you comment on what happens as a little more about as the number of felicities, negative felicities, increases?
Okay, so what's special about the all plus is that the factorization is simple. And if you increase, let's say, if you go at one loop, you go to 1 minus, or at tree level, you go to NMHB and beyond, then the factorization structure is more complicated. And we understand kind of in general terms how this translates there. There is a similar kind of structure. It's just more complicated. We haven't really explored it. There are some very preliminary results, but again, in some of these cases that we've looked at, there again, first of all, the relations have to be there, but they turn out to be of relatively low degree, way lower than you would expect from the general existence argument. And in fact, the Copenhagen people, I don't recall that they classified it completely, but they did show, for example, that for the tree level MHB, there are additional identities beyond BCJ, and they follow from the same kind of construction. So I don't know if that quite answers your question or not.
Questions, and let's take David again.